In today's class, I'm going to be teaching advanced divisibility. Okay, so first, we can start with the division algorithm. Some of you guys might have, like Amanda, I think you missed this class on Sunday, so I'm just gonna teach it again. Okay, so the division algorithm is essentially for any pair of integers, like A and B, there is two unique integers called Q and R, which are the quotient and the remainder. And these four integers will satisfy the following formula, which is A equals BQ plus R, and R is greater or equal to 0 and less than B. So what this means essentially is that A is the dividend and B is the divisor and Q is the quotient and R is the remainder. So essentially, our formula here is just dividend equals divisor times quotient plus remainder. And here we have an example. We have 62, which equals to 6 times 10 plus 2, which is, this is the dividend. This is the divisor, quotient, and remainder. Okay, so that was starting off pretty easy. So moving on. Next, we have the Euclidean algorithm. So I'm sure a lot of you guys have heard of this before, even if you don't know about it. Essentially, it's just to find the greatest common divisor of two natural numbers of A and B, where A is greater than B. Remember that A is greater than B. So for this, for the Euclidean algorithm, essentially you're just applying the division algorithm over and over again until the remainder's like 0. So here, as you can see, we have A equals BQ1, which is quotient 1, plus R1, which is the first quotient and the first remainder. So this is the first time that you apply it. And then you take the divisor and it becomes the dividend. And then you take the first remainder and that becomes the divisor. And then you get a new quotient and a new remainder. So this is the second time you're applying it. And then you repeat the process all over again. You take the first remainder and then that becomes the dividend and the second remainder becomes the divisor and you get a new quotient and a new remainder as well. And then you just keep going until you just have no remainder. So here we have an example. It tells us to find the GCD of 110 and 380. So as you can see here, we can start off with 380. Oops. 380 equals to 110 times 3 plus 50. So we take B here and we bring it down as our next dividend. And then we take the first remainder, which is 50, which gives us 50 times 2 plus 10. And then, sorry, let me move this up really quick. Oh my God. We just, let me move this up. And then after we've done the second division, we take the divisor again and it becomes the dividend. No, we take the first remainder this time. And yeah, now we have no remainder. So essentially the greatest common divisor is 10. And it's not 5 because this is also a divisor, but it's smaller than 10. So that's not our GCD. So do you guys have any questions about the Euclidean algorithm? No questions? Okay. So next we have the extended Euclidean algorithm. This not only finds the GCD of A and B, but also finds integers x and y such that ax plus by is equal to the GCD of A and B. You guys will learn that this equation here is actually a Diophantine equation, and it's part of the Bezout's identity, but I don't think we'll be talking about that today. So here we have an example of it. We have 15 and 25. So here, it's just the same thing as a Euclidean algorithm here, so I won't explain it. But now we use back substitution to express 5 as a linear combination. So essentially what this means is first we start off with 5, which is equal to 15 minus 10. So 5 minus 10. And then we take 10, and essentially we're just going backwards. So we have 10, which is equal to 25 minus 15. So essentially here, we can all put this into an equation, which gives us 5 equals 15 minus 25 minus 15, which is 10, which is equal to 2 times 15 minus 25. Okay, so we turn this into a linear combination by inserting it into this formula here, where x is 2 and y is equal to -1 because we're subtracting 25 here. So this becomes 15x plus 25y, which is equal to 5. And x is equal to 2, and y is equal to -1. So yeah, does anyone have any questions about the extended Euclidean algorithm? No questions? Okay. Okay, so next we have some practice problems. I want you guys to try these problems. So I think I'll give you guys like 5 minutes for this. So yeah, I'll see you guys in like 5 minutes. Okay, so next I'll be uh, okay, so I'm assuming you guys finished the practice problems now. So these are the answers. Um, since there's not a lot of time left, I'm actually gonna just let you guys look at this yourselves because if I explained all three questions, it would take a while, and we still have a lot of stuff to go through. So next, I'll be talking about divisibility in polynomials. Fred talked about this in his class yesterday, so I'm assuming you guys were all there. So it should be easier to understand now. So essentially, um, a polynomial is well, polynomial is divisible by another if there exists a unique polynomial such that um, px, the first polynomial, is equal to dx times qx. So essentially, px is the dividend, dx is divisor, and qx is the quotient. If if like the division results in a remainder, we call that Rx, and it's essentially just the same formula as the A equals EQ plus R formula, except it's just for polynomials. So here we have the polynomial division algorithm. It's just the same as the division algorithm, but for polynomials. You can tell from the title. So given two polynomials, px and dx, um, the degree of px has to be greater or equal to the degree of dx. The formula is just px equals to dx times qx plus rx. And I already explained before, but qx is the quotient, rx is the remainder. But the degree of the remainder has to be less than the degree of the divisor. So I have this small example for you guys to try here. Um, I'll give you guys like 3 minutes for this. It shouldn't be that bad. So I'll check up on you guys in like 3 minutes. Okay, so time's up. All right. So if Fred did not explain to you guys already, we can use polynomial long division to solve this. Let me scroll down. Um, so we can just write this as x minus 2 divides x to the power of 3 minus 2x squared plus 4x minus 8. Okay, so here we have it in long division form. Let me just move this down. Okay, so essentially, we can first start off by canceling the first two terms. So all you have to do is just multiply the divisor by x to the power of 2, which gives us x to the power of 3 minus 2x power of 2. And this whole thing just cancels out, and we're only left with this. So next we just bring this down here, and we have 4x minus 8. And now to cancel this, we're just going to multiply the divisor by 4. And this gives us 4x minus 8. So now we can just cancel that by just subtracting it, and our remainder is 0. So that was a pretty simple example. So essentially our quotient is qx is equal to x to the power of 2 plus 4. And Rx is equal to 0, which means that x minus 2 can perfectly divide our polynomial x to the power of 3 minus 2x to the power of 2 plus 4x minus 8. Do you guys have any questions about that? Oops. No questions? Okay. Moving on. Here we have the Euclidean algorithm for polynomials. Again, this is just the same as the other simple Euclidean algorithm for integers, but this is for polynomials. So it's just the same process. We just divide px by dx and get rx, and then we once again just replace px with dx, and then you divide again. Sorry, you replace px with dx and dx with rx, and then you just repeat the process until the remainder is 0. Just like the other Euclidean algorithm for integers. So here we have a simple example. This is just x to the power of 3 minus 4x, which is px. And dx is equal to x to the power of 2 minus 4. So here we have our dividend and divisor. So once again, we can just put this into, we can once again just put this into long division form, but it's not really needed, but I'll just do it so it's easier to understand. X minus 4x. Okay, so here, all we have to do is multiply our divisor by x to cancel this out completely. So here we have x of have 3 minus 4x, which just gives us 0. So that just leaves our quotient as x. You don't really have to write the plus 0, but I just wrote it. And our remainder, Rx is 0, so our GCD is essentially just, oops. Our GCD is just x to the power of 2 minus 4 because there was no non-zero remainder before we reached 0. So the GCD is just the original divisor. And here we just have our theorem. It's just the same as the one for the integers, so I'll just skip this. Okay, so here we have another example. Oops. I want you guys to use polynomial long division to do this actually, or you can use the Euclidean algorithm. Like any is fine. For those of you who know, you can also use synthetic division. So I'll give you guys like 3 minutes to try this as well. Okay, guys, it's been like 3 minutes, so I'm gonna start explaining the solution. Um, okay, so essentially there's a really long solution here, but here we can just use polynomial long division again. Like, um, so our divisor is x to the power of 2 minus 5x plus 6, and our dividend, oh my god, our dividend is x to the power of 3 minus 6x squared plus 11x minus 6. Okay, here we have our equation, our expression. Um, Let me just move this down really quick. Okay, so first we can start with canceling this leading term right here. So as you can see, we just multiply x to the power of 2 by x, and we get x to the power of 3. So this just cancels out. And then we multiply x by the rest of each one, which gives us negative 5x to the power of 2 plus 6x. So here we just subtract everything and we get x to the power of 2. Sorry, we get negative x to the power of 2 plus 5x. And now we can bring down the negative 6. So here comes our second division. Now we have to multiply, now we have to multiply again, but like this time, as you can see, these are literally the same equation, but the signs are flipped. So all we have to do is multiply by -1, and then we get the same equation, minus 6. And then we subtract, and then we have 0. So as you can see, now that our remainder is 0, you guys remember that the GCD is just the last non-zero remainder of the division, which is this right here. So this is our GCD, which is -2 plus 5x minus 6. Do you guys have any questions about this? No questions? Okay. Okay, so here we have this polynomial remainder theorem. The remainder theorem states that for any polynomial px that is divided by x minus a, which can be any integer, the remainder is p of a. So essentially, you just put the value of a into the polynomial px. For example, in here, we have this polynomial right here, and our divisor is x minus 2. So we just evaluate p2, which just gives us 2 to the power of 3 minus 2 times 2 to the power of 2, plus 4 times 2 minus 8, which is just equal to 8 minus 8 plus 8 minus 8, which is 0. And since our remainder is 0, it just means that x minus 2 divides px exactly. So I have another I'll just explain this little example for you guys because this part is pretty easy and we're running out of time and I really want to get to the math contest questions. So here we have x to the power of 3 minus 3x plus 2 divided by x minus 1. And we just substitute 1 into px, which just gives us 1 to the power of 3 minus 3 times 1 plus 2, which equals to 1 minus 3 plus 2, which is equal to 0. And that means that x minus 1 is a factor of px because it divides into px perfectly and our remainder is 0. So this is just the factorization of polynomials. This part I think you guys can look at by yourselves because there's not really any need for me to explain this because it's not really like it's not really relevant to what I'll be talking about today. So these are just some practice problems. You guys can do these by yourselves at home after this class if you want. So okay, here um I'll just skip this problem because these are just some examples. You guys can do these by yourselves if you want. Okay, so here we have the question that I've been wanting to explain to you guys. It's an AIME question, which means it's past AMC 12. So yeah, you guys can try it if you want. But I'll give you guys like 3 minutes for this. So I'll see you guys in 3 minutes. Okay, so it's been like 3 minutes. Hopefully you guys have tried this, and yeah. Okay, so essentially, we can also use polynomial long division for this. As you can see here, I just use and put the divisor and 3 plus 100. Okay, so here's our expression right here. So first, we can just cancel this leading term by multiplying everything by n to the power of 2. So we got n to the power of 3 plus n squared. So now that our n to the power of 3 has been canceled, just cancel that. We're left with subtracting these. This can't really be subtracted, so we just write it as -10n squared plus 100. So our next goal is to cancel our new leading term, which is -10n squared. So essentially we can do this by multiplying our divisor by -10n, which leaves us with -10n squared minus 100n. Okay, so here we have that, and this once again just cancels out, but we are left with, sorry, let me just move this really quick. Okay, so we're left with 100n plus 100 as our remainder. So now to cancel this, we multiply our divisor by 100. So our quotient is now n to the power of 2 minus 10n plus 100. And this gives us 100n plus 1000. And once we just subtract everything, this comes 0. And our remainder is -900. And our quotient is n to the power of 2 minus 10n plus 100. So I don't think you guys should have any questions about the long division part because we already went through a bunch of examples. But that's not all. Here, now we're finding the GCD. Now we're finding the GCD with our remainder. So we plug everything in to this formula right here that I talked about earlier, our A equals BQ plus R formula. And we essentially get n to the power of 3 plus 100 equals n plus 10 n squared minus 10 n minus 100 minus 900. Okay, so here we have everything plugged in to the divisibility formula. So plugging this in to the RGCD formula, we get n plus, sorry, let me clear this. We get n plus n equals GCD n to the power of 3 plus 100 and n plus 10. This is the first part of our formula here, which brings us to our next part of the formula, which is GCD negative 900 and n plus 10. Anyways, so this is our second part of the formula. So this also brings us to the next part, which is GCD 900 and plus 10. The reason why that we have negative 900 and 900 is because, like, the factors don't, like, the factors of these are the same, so the sign doesn't even matter. So now that we have everything plugged into the formula, we find that when n plus 10 is equal to 900, the GCD is at its greatest value, and correspondingly n becomes the largest value. And when n plus 10 equals to 900, n becomes 890, which brings us to our solution. Because the question asks for the largest positive integer n, where n to the power of 3 plus 100 is divisible by n plus 10. So here we have our solution. And the greatest value is that when n is equal to 890.